Okay, in this video, we're going to look at an exact differential equation, but I have a side blank slate to the side because I want to give a little bit of background of what exactly this process is. So to be exact, the claim is that you take, so many textbooks call this m, this function of xy, right? We may not have both x and y, but we might. So we call it a function of xy. We often just call that m, okay? But it is a function of xy. And then this piece in front of the dy we call n, which is also a function of xy. And to be exact, the claim is that if we take the partial derivative with respect to y, so we look at m, and we take the partial with respect to y, that we should get the same thing as if we look at this function of xy n and take the partial with respect to x. So why is that the case? And so we're going to take a look at constructing this on the side here with an easier example. But basically what kind of gives that out is we're doing partial x, partial y, and this has this dx, so it was a manipulation, okay? All right, so here's my example. First thing, it claims any general solution, okay? Any general solution to a differential equation can be written in the form, now we're talking only two variable, right, x, y, can be written in this form. This function equals a constant. All right, fair enough. A general solution, it might only have, right, y and x to any degree. Let me just backtrack there. It could have y and x to any degree. It could be composed of x's and y's being multiplied, kind of like our exact differential equation there, or not, right? It could be as simple as just a linear function or whatever. So what I am going to do is just kind of look at this example. Say we had xy equals 1. I know that we could solve that, right, as y equals 1 over x, but the point is that say that was our solution to a differential equation, we can group all the variables on the left and set it equal to some constant. That constant might be 0, right? In this case, 0 would be boring, but never know. Okay, so the idea is, well, if I had this general solution and I was creating a differential equation, right? Maybe I did derivative with respect to x, maybe I did it with respect to y, maybe we did a second derivative or partial derivatives, right? It won't matter. The criteria for exact differential equations will take care of that criteria in order to use this process. Quick side note, if this is not true, okay, if that's not true, it might be able to be manipulated to be exact. Okay, so if not, can we make it exact? Well, that is a whole nother process in itself. So that's another video. Okay, we're going to just look at this case. So let's say we took derivative of xy equals 1 with respect to x, okay, of xy. So we're going to do it both sides, right? So of xy and of 1, derivative of any constant is 0. Derivative with respect to x, you know what? Let me sidetrack, sorry. Not just derivative with respect, oh yeah, that'll work. My bad. Okay, with respect to x. So we have a function, right? We have product rule, f times g. So with respect to x, this would be f prime g, so 1 times y, plus, now leave f alone, right? F prime g, so x dy dx. So one manipulation tactic was like to, even though dy dx means rate of change, or it means a derivative, we investigate differentials, and the fact that this works, we multiply everything by dx, right? Like, it's weird, but because it works, we often do this to solve differential equations. So why I wanted to do that here is because now this is in that form, right? Dx times y, and then over to the right it would cancel, and we just have plus x dy. An exact differential equation to use this process needs to first be in that form, a function of xy dx plus a function of xy dy. Okay, we're good. And it must equal 0, we're good. So this is in the exact form. So now what we want to think about here is, like, what does this process entail? So we're going to look at both the right-hand side and begin the process on the left-hand side. So first let's look, all right, is it exact? It's in the form. Is partial m, right? This is m, this is n. Is partial m with respect to y, well, partial m with respect to y is 1, equal to partial n with respect to x, which is also 1. So yes, it is exact, right? Let's look at this more complex one on the left. Partial m with respect to y. So we would get, again, product rule, right? F times g. So with respect to y, we have 1 exy plus y. Now, the derivative of exy with respect to y would be x exy, right? EU du. Think EU du. Okay, partial n. So now the question is, does that equal partial n with respect to x? Well, derivative of 2y is 0. And then again, we have product rule. Derivative of x is 1 times the xy, looking good so far, plus x, derivative of g with respect to y is y e to the xy. Okay, again, EU du. All right, we're good. That example is exact. All right, so the next idea is we take one of these, whichever side, like whichever one looks easier. Sometimes one may look easier than the other. In this case, I mean, they're tie, right? Like no, I would say M looks a tad bit easier because we have a 1. Okay, so what do I mean by easier? We're comparing these two, M and N, and we need to either integrate M with respect to X or N with respect to Y, all right? So in this example on the right, like, really wouldn't matter, right? Get the same thing. So for consistency in this video, we're going to integrate the m with respect to x. Now, let's take a step back here. Why is that the process? So what we're trying to do is find the general solution, right? In the right-hand side, I know it's xy equals 1. So what we're saying is I'm going to take this here and integrate, but then I don't know my constant, and I'll get some function in which I don't know the constant. But then if I do derivative, I should have the entire piece. So let's take a look. The m has a dx, right? Y dx. So if I'm calling my function f, so I took some derivative of my function f, and I have y dx, right? If I integrate both sides, I then have f, right? Undo derivative here, I have f, but on the right-hand side, I have xy, again with respect to x, right? We have xy, but I only took care of the derivative of x, and this exact equation still has this dy over here. So what is that saying? That's saying I had some extra function of y, right? Instead of adding c, it is a c, it's an unknown, but I knew it was a function of y. Because if it was a function of y with respect to x, right there's my dy there. Okay? But we could have chose to do n, and then I would have needed to integrate with respect to y. Okay, I'm choosing m on the left because, again, it's easier. That's the only reason. I have a 1 rather than a 2y. But it would have worked. So this d of f, my end goal is to get f, a function of xy, is equal to that 1 plus ye xy dx. Okay, and we are integrating to undo the derivative. So therefore f is equal to, again with respect to x, right? So that equals x. This is kind of weird, but this really does fit EU du, where I'm saying u is xy, du is y dx, right? So I have y dx, there's my du, and then here's my EU du. And the integral of EU du is just EU. So that's why this integral is e to the xy. Okay, again, plus some function of y that I don't know yet. But in this case, to form this exact differential, what we can do now is take the derivative with respect to y. Okay, why is that? Because then we are trying to find g prime of y, and I could find that function. Okay, it's kind of weird where we are constructing this function f by integrating, then derivative, then integrating, going back and forth until we have a general solution. Okay, so let's write this down here. We just integrated. Okay, now we are going to do derivative with respect to y. Okay, dy of f. Let me change that color. Just trying to stay consistent here. I didn't change f. Okay, and then we're going to do the, no. Derivative of y. Derivative with respect to y on the right. Now, the derivative with respect to y of f, right, we just called that n. So really what we're doing is taking m, integrating derivative, and arriving back to n. Okay, with respect to y was n. Okay, by definition, right? Now, derivative of the right-hand side with respect to y. So here we have x and then g prime of y. But n we called x, right? So let's finish the right-hand side really quick. This is x. I want to do that in purple. Again, that's what we called it up above. N was x. So therefore, if that's x and it equals x plus g prime of y over here, we would subtract x on both sides, and then we know g prime of y is 0. But if a derivative is equal to 0, then I know that that is constant. Okay, that means g of y was constant. And if g of y is constant, we can look back, right? Ultimately, we found f. It was xy plus some function of y. So if f is xy plus some constant, because that's all I got, going back to the original, right? We said once we have f as a function of x and y, we could just set it equal to a constant, and therefore this is equivalent to just saying xy equals c. And we knew above what c was, right? Like I know I started with a constant, but point is this worked. If I knew what c was or the initial condition, we now have exactly what we started with. Okay, it's a back and forth process. So let's go back to the example, finish this one up. Again, we integrated with respect to x, and now we need to do derivative with respect to y. Derivative with respect to y, both sides. All right, what does that yield? Remember, we define this as n. Derivative with respect to y on the right, we get, let's see, derivative of x is 0. E to the xy with respect to y would be x exy, eu du, plus g prime y. But n was 2, so let's make that substitution. N was 2y plus x exy. All right, simplifying, subtracting, right? Those cancel. 2y is g prime y. And we need to undo a derivative. Well, g prime is d dy of g, right? So we could think of this just integrate, but we moved the dy over there so that we know g of y, integral of 2y is 2y squared over 2, so y squared, plus c, right? We don't know what c is. In the right hand side, we knew g prime was 0, so g of y was just a constant. Now it's not. And then again, we had defined f up above, right? F is this. Well, I now know what g of y is. It's y squared plus c. And skipping a step, just to I explained over there how to define f. Then I know if I plug y squared plus c in here, that's equivalent to just saying x plus exy plus y squared equals c, because I said equal to 0, subtract c, but c is constant, doesn't matter. Again, we know we could define any general solution f of xy to equal c. So here's our f of xy. There's the right-hand side, c. I hope that kind of helps seeing really the process, kind of what's going on of going back and forth. Okay, it's important that it meets the criteria to be exact, otherwise this process won't work. And unless we can make it exact, again, that's a video in itself, quite lengthy.